So what I'm going to do is go through what computing on encrypted data is, what are some of the constraints, what are some of what the kind of things you might have to think about when you want to deploy it. I'm not going to talk about theory because theory bores me. I'm old, I can't do theory, that's for youngsters. And what I'm also going to do is point out how this relates to some of the talks coming up later on. So you're also going to see pointers to some of the stuff you'll see later on, which will act as a taster, so you don't all disappear after the coffee break because you've just seen me and you've only turned up to see me. Okay, so this is the difference. Right, so okay, so when we started looking at computing on encrypted data many minutes ago in Bristol, in the UK, if you want to go, I've got some technology, I want to use it, who are you going to send it to? You're going to send it to the people who have the most money. And the people who have the most money in the UK is what we call the city, which is the banking industry or the financial services sector. So I went and talked to a bunch of, it's quite interesting, you phone up, I don't know, anyone from Hewlett Packard here? Anyone from IBM? Good, I can insult them to my house. Right, you phone someone up from IBM or Hewlett Packard as an academic, and you phone them and say, I've got some really cool piece of technology. You go, yeah, and then you might, if you're lucky, manage to talk to an engineer at some point, right? But if you phone up, I found rather interesting, you phone up very big people running very, very big markets in London, which are trading billions of dollars a day, and you phone them up and go, I've got a cool piece of technology, they invite you to a board meeting. Okay, so here you are, you sit on the top of this huge skyscraper in London looking out and you've got an amazing view and there's people in board meeting and they are bright. They are very bright. That's the reason why the stupid people go work for HP and IBM, right? Because the clever people have gone to work for the investment banks. And then you kind of give them, what's your story? You know, how are you going to motivate investment bankers to be interested in this technology? This is it. You give this talk and suddenly every single investment banker in the room is awake. And not only are they awake, they go, shit, I mean, this is really cool. Right, so they're going to go for lunch. Right, they're just, it's whatever the time of the year is, it's June, they're just about to get all their bonuses, well, they've just got their bonuses, and they're going to go out to celebrate getting their bonuses, right? So, one's going to spend their bonus on a Ferrari, one's going to buy a $200 million yacht, one's going to buy, I don't know, some poxy little country somewhere, and one's going to buy something else, right? So they want to know who's got the most money, because the person who's got the most money should pay for lunch, obviously, yeah? Because you couldn't have the poor one who's only going to buy the Ferrari paying for lunch, right? So they've got to decide. So they want to know who's going to pay for lunch, and it should be the person with the biggest bonus. But of course, they don't want to reveal what the size of their bonus is. Because if they reveal the size of the bonus, you know, you've got a bit of, you know, that's not really good for office politics, really, going forward for the next year. So you've got to keep your value of your bonus secret whilst computing who should pay for lunch. And at this point, all the investment bankers have suddenly woken up and go, shit, we have that problem every day. So, anyway. So, what you want to do is, you think about it, you've got 4 people, and they've got some money, and they want to compute a function. The function they want to compute is argmax, basically. They want to compute the value of I such that xi is bigger than xj for all other j. Okay? This is what's called the millionaire's problem for the 2-pi system. It was introduced by Andy Yao. He won a Turing Award for this. He won a Turing Award in the past, but he didn't win $1 million for this, so that's not a good strategy. So the best strategy is to win Turing Awards now, not in the past, because there's now more money associated to them. But anyway, so you want to compute this function. So all we want to do is compute a function on secret data. Now obviously, suppose this guy's the richest guy. He will learn he's the richest guy. This guy will learn he's got a less of a bonus than this guy, but doesn't know what the bonus is. All that this guy learns is his own bonus, which he knows, and that this guy's got paid more. Doesn't learn whether this guy's more or less than him, or this guy's more or less than him. So that's what we do. So you compute the answer, and the only information that's revealed is what you could deduce from the answer itself. Okay? So, right. So, one way of doing this is we have a bank. Sorry, not a bank, a god-like figure, which in the bank is kind of like something better. So a god-like figure, okay, so we have this god-like figure, and they all basically pass their information to the trusted party, the god-like figure, and the god-like figure computes the answer for them. Okay, so that would be the traditional way of doing things. You have a trusted third party to do things. However, we're cryptographers, and we don't believe in God. So what we want to do is we want to replace the god-like figure with a protocol. And that is essentially what computing on encrypted data does. So if you take nothing away from today, you can say we have a protocol to enable investment bankers to decide who's going to pay for lunch. Okay? Now, when we started doing this in the, when did we start doing this? In 97-ish? Yes, 97-ish. We could actually, for two parties, it took us half an hour to compare two 16-bit numbers. So we couldn't even do, you know, we couldn't even compare the bonuses of PhD, well, maybe PhD students, but we certainly compared the bonuses of professors, okay? Because there's only 16 bits. However, since then, instead of going 30 minutes for comparing 16-bit numbers, we can now compute incredibly complex functions incredibly fast. So the change in this technology from 97 up to now has been absolutely spectacular. Was it 90? No, I've got the wrong year. 2007, not 97. 2007. In 10 years, it's gone spectacular. Yeah, not 20. 20 would be boring. Yeah, it's 10 years. It's gone from very, very slow to incredibly fast. So fast that you've got a bunch of companies this afternoon telling you what amazing things they're going to be doing. Okay. So what do we try? So if you want to put this into the kind of triangle of information security, is that generally in cryptography, in the past, we have been interested in data and transport and data at rest. So if you're sitting in a company, your only use of cryptography is data and transport. On a bank, I always talk banks because I'm English. So on a bank, I want to trade credit cards from A to B data, so therefore I'm going to TLS encrypt it. Yeah? So this is what data and transport does. Or I'm coming up with a tunnel, so I'm going to put it over IPsec or whatever. So I'm encrypting data as it goes from A to B, or if I'm in the past, I'm encrypting the Enigma traffic. Yeah, so I'm taking the Enigma machine and I'm using that to encrypt the traffic. Okay, slightly more modern from in terms of actual deployment in organisations. We now encrypt data at rest. You know, almost all laptops, if your company is very sensible, would hard disk encrypt the laptop in case you leave it on a tray. You'll have your database encrypted, you'll have your HSM key storage. If you're in a bank, you'll have an HSM, which is like this horrible thing, which we'll talk about later, where you store things, and that's where you store things encrypted. Now the thing is with data, it's all very well to send it, and it's all very well to store it, but there's something you want to do with data, which is actually use the bloody stuff, right? So what we haven't addressed is actually data during computation. So this is what this technology actually does. It addresses data, the security of data during computation. So that's what we're trying to secure. And there are a large number of applications. You can think of voting. Voting is an application where you take data, you want to keep it private, you want to compute a function on the data. GDPR, we have private data, we want to compute something on the private data. Genomics, everyone's got. Don't worry about taking pictures, but I'll do the slides for you all later, so don't worry. So genomics, you want to have DNA data and you want to do some computation on it. We'll talk about public policy stuff a bit later on, and some citizen privacy stuff as well. So there's all loads of applications of this technology, and you can just list them, and we're going to list a bunch later on. Okay, so there are two technologies you need to consider. There's MPC, which is multi-party computation, and fully homomorphic encryption. Now you might have heard of fully homomorphic encryption because the tech press has been really, really big at promoting this and whatever. However, the more practical technology is MPC. But to show you that fully homomorphic encryption is not totally slow, we've got Pascal later on this afternoon who's going to show you how you can use fully homomorphic encryption and do some really cool stuff in neural networks. So we've got that. But the main difference is in multi-party computation, the things in the title, multiple parties engage in a protocol together. And the take-home message you should have, it's relatively fast in computation, but it costs you in communication. So it burns up your communication links, okay? But it enables a large number of applications, which we'll see later. In FHE, it's the other way round. It's very slow in computation, but relatively cheap in communication. So you kind of have one side or the other. And it's only possible currently for simple functions or well-tailored examples, which we'll talk about a bit later on. But you will kind of demonstrate these differences in a number of applications later. But there's two types of technology. You must never get the two confused, because you see when you talk to some companies, they get the two confused and it gets into a mess. So one way to think about this, which I've borrowed from Cybernetica and from others, is you have a bunch of parties. You have input parties, they're the parties who start with the data. You have parties that are processing data, and you have parties that get the data in the end, okay? And if you think about these as three separate entities, you can now start looking at the space and working out what your different scenario is going to be and whether that scenario maps to what the issue you have in your organisation. So a traditional computer is that I type stuff in the computer does the work, and the computer gives me the answer. Yeah, that's all three parties are the same computer. Okay, that's like computing 101. Yeah, programming is C. Oh, they're all the same thing, right? Now you might have many different input parties sending data to an output party, a processing party, and then someone getting the result. This is like a voting application. Yeah, I've got many people vote. Someone tallies the vote, someone gets the answer. That's a voting application, yeah? If you think of the input parties and the output parties, then that's a cloud scenario. What I do is I have some data, I send it to the cloud does the computation, the cloud sends the data back to me. Yeah? So this is a cloud application. So you can see you can capture lots of applications with these pictures and kind of help you get your way. Right, so multi-party computation is, we could have one input party, say they could send their data, their private genome data, could be computed on by a bunch of parties, and then someone else, say some medical company, gets the answer. So none of these people learn the genome data, and this guy gets maybe the output, whether he's a good person's a good candidate for a drug trial or something. So this would be a sort of standard multi-party computation, and then where those red people are many threes, you can then insert that here in any of these pictures that you want. You could have many people sending it up to the cloud that's distributed and comes back. Okay. Okay, so now in fully homomorphic encryption, you only have one computing party. There could be one or more output parties, but in some sense, if you only have one output party, these people must be different. There must be a distinct separation here, because this guy basically decrypts what this guy's got. So if this guy could decrypt it, he could decrypt the inputs, so it's kind of a bit silly. So this is the fully homomorphic encryption example, and again, we'll see that in an application that we've developed in Leuven in a short while. Okay, so let's go a bit of history. So in fully homomorphic encryption, the input parties encrypt their data. So someone encrypts the data and sends it to you. Then the computing party evaluates a function on the data and obtains the encrypted result. Okay, they obtain the encryption of the result. So could be everyone encrypts their vote. The computing party sums up the encryptions in some way and gets an encryption of the result of the election. This is then passed to the output party who decrypts and obtains the result of the election. Okay, so that's how FHE works. So it's like you're outsourcing data, you're outsourcing computation. So this is why the press picked up on it, especially because IBM promoted it, is that the idea is you could encrypt your Google queries, and Google could do a search without actually knowing what your query is. It would be really cool if they could do it, but FHE isn't that powerful at the moment. So the first scheme was, it was originally proposed in 1976-77, but it wasn't until 2008 that the first scheme was actually produced that you could even think about implementing, not even think about implementing. I mean, the original scheme was so complicated, I think only 3 people on the planet understood it. And then I was staying, where are we? In a little flat over there for 2 weeks in Leuven, and then during my 2-week stay, or 3-week stay, where it was in Leuven, over there, me and Frey, we implemented this first scheme, and we gave the first implementation of a homomorphic encryption scheme, and we could actually multiply and add numbers together, which was kind of cool. It was kind of really amazing that you could actually do anything. So in theory, you can compute anything, okay? And in theory, this anything is only with a small extra cost. The trouble is this small cost is not that small. So it's asymptotically small, but not actually small, really big. Okay. So in practice, if we're not talking about, in a gazillion years' time, when computers are much more powerful, in practice, actually doing anything is really much more difficult. So you have to really fine-tune the application. So whether FHE is useful for you really depends on your specific application domain, what you're trying to compute. So It's not a magic bullet. It looks like it's going to be a magic bullet, but it isn't. But it is useful in many applications, and we'll see a few this afternoon. MPC, on the other hand, is this kind of paradigm. You have many input parties, a bunch of people are computing, and a bunch of output parties. And the idea is that these computing parties can't access the data if they don't collaborate. So if you suppose we had one of these was Microsoft, one of these was Amazon, and one of these was Google, we can kind of assume that they don't trust each other, and they're certainly not going to, reveal information to each other. So you could, as long as you trust that, say, Microsoft is not going to be a bad guy, no matter how bad Google and Amazon are, your data is secure. But that would be my trust assumption, that I like Microsoft. You might prefer Google, and you say, I trust Google, I don't trust Microsoft. But that's fine, because your data is secure as long as you trust one of them. So the idea is that your data is secure as long as you, one of the input parties, trust one of them not to be a bad guy. Okay, so that's the idea of multi-party computation. What we do is we get security by having many people, many locations of the data. And again, we'll see applications of this in different scenarios. So if you map this back to dining bankers, in the dining bankers example, actually the input parties, the computing parties and the output parties were all the same. But they engaged, that each one had their own input, they all together computed, and of course if they're computing, they trust themselves. So they know that their data is secure because the MPC protocol guarantees that as long as you trust someone, then your computation is secure, and because you are one of the people doing the computation and you trust yourself, your data is secure. So that's another sort of way of thinking about it. Okay. So to compare, what the point is that with FHE, is the thing that made it hard to produce in practice was that we only had one computing party. And what we do with MPC is we trade computation for communication. So this, I have to do a bit of theory, so I'm going to do a bit of theory here. So this is true in standard complexity theory. If we have, if you talk about standard complexity theory, you talk about NP. Everyone, who doesn't know what NP is? Good. No one wants to admit. Right. So, right, I like it. Brave audience. Okay. So you have so NP is the set of basically things that you can prove without interaction. Yeah. So you create. I'm this almighty professor at the front who can prove anything. So I send you a proof, and you can verify it very quickly. This is the NP language. Yes. You're the measly students who can verify things. I'm the God-giving professor who can come up with proofs. Now, that is just a one-shot thing. If I allow you to ask questions, God for sake, right? Then, especially in the lecture, students ask questions. Oh my God, right? So if the students ask questions, then we have an interactive protocol, and I can actually prove to you more than if I had NP. This is the statement that IP, interactive protocols, is bigger than NP. In fact, IP is the whole of P space. IP is huge. So in standard complexity theory, allowing communication allows us to compute more. And just as that happens in complexity theory, so it happens in security and cryptography as well. If I allow communication, I can compute more, and I can compute stuff better, and that's what MPC does. The key point is we have more than greater than or equal to two parties, but we do use a lot of communication, and if you kind of do the cost metrics, that asymptotically Moore's law always beats the increase in whatever the law is for Wi-Fi connectivity or bandwidth connectivity. Bandwidth always goes up slower than computing power. So eventually FHE will win, okay? But where we sit now, and probably for the next 300 years, at this rate, the MPC for general computations will, on the assumption there's no other improvement in protocols, MPC will always beat FHE, okay? Okay, so we have some examples. So I've just rubbished FHE. So I'm now going to tell you, so anyone got any questions about the difference between MPC and FHE as we go? No, so I'm going to go into a bunch of examples. See what we are. Okay. So the first example is one we did in Leuven as part of an EU project called HEAT. And this was, we're looking at privacy in the smart grid. Okay? So this we did with homomorphic encryption. So what happens is that you're doing some stuff at home, like you and me, or you're actually computing stuff at home, but there are other uses of electricity. And then you're using electricity at home, and you send stuff to the network, and the network wants to respond. And this is the idea: is that you can, if you knew more about electricity consumption, your power plants could respond better. You wouldn't have to have such, the expensive. You could keep the base load and then the stuff with the peak load, which is basically turn on a hydroelectric plant, something can be much quicker. Okay? But then, so you put your oven on, your refrigerator's on, and it goes, so you've got different power consumption. Now the problem is if you send that information directly to the power company, you're at home, your oven's on, usually when you're at home, your oven's on when you're at home, yes, but then when your oven is not on and there's no lights on and it's the middle of the day, maybe your house is empty, that would be a good time to rob. So if you distrusted your power company, they would know when to rob your house. Okay. Alternatively, they could find out that anything, all sorts of things about you. It might be the type of stuff you're cooking consumes more energy than something else. Therefore, they can deduce something else about you. So to protect your privacy, you probably do not want to send your power data to the company. But the company doesn't really want your power data. It actually just wants sort of aggregate data to be able to do statistics, to be able to respond. Because it doesn't really care about your little house. It cares really about the set of houses supplied by the substation. So, we would like to encrypt the power data such that the power company cannot have any information about your individual usage, but can still extract sensible statistics from it. So how do we do this? So what we actually did this is that we, what you want to do is you send the data in, and then you have a machine learning model that predicts what the next bit of power consumption will be, given maybe the input from a few houses or a street or a town. Okay? So you have a machine learning model which is done by a neural network, and you want to evaluate the neural network efficiently. So what happens is that we have what we did with in the HEAT project for this smart meter data, we came up with a special neural network which could predict energy usage using data from the Irish, who made a bunch of data for smart meters publicly available to play with. And you can evaluate a neural network which predicts what the power consumption will be of a particular group of houses for the next time period. And you could evaluate this neural network, because it was specially designed, you could evaluate this neural network using FHE in an efficient way. So, this was a neural network that you could actually evaluate with FHE, specifically because it wasn't a general neural network, it was a specially designed one that was FHE friendly, if you want. And it was basically a polynomial. So you could evaluate, so you had two encrypted inputs, and you could evaluate a polynomial, which is a nice thing to do in FHE land, so we could do that. So how does this map into the application domain? So you would basically have an apartment block which would encrypt the power data. Then for the whole apartment block, it would be summed under the encryption. It would be passed to the power company, which would across the wire, this encryption, which you could then pass through the neural network, and it would then give an encrypted forecast, which someone else could then decrypt to obtain the result of the. So you have some computation done at the apartment block, some computation, encrypted computation done at the apartment block, some done on the using the neural network in the encrypted domain, and then someone would decrypt it to work out what was going on. Okay, so that was an FHE owned example, and you'll see another example with neural networks later on this afternoon. So that's a kind of cool example. Okay, so another one we did, and this was quite interesting because we did one application with MPC and one application with FHE, so you can see the difference. So what we have is that we want to do a sort of what's called a genome-wide association study. Okay, so You have a bunch of DNA, you want to find an association between certain aspects of the DNA and the control group and the group of a disease. You basically got two groups of people, the healthy people and the bad people, not bad people, unhealthy people, and you want to work out if there is a relationship in the DNA sequencing between the two, because this will be able you to predict diseases or maybe responses, cures. Now the problem is that of course you don't want to give your DNA sequencing up, but you do get social good out of this. So we came up, it turns out that this seems really complicated for DNA sequence, but actually all you're doing is a very simple statistical test between a healthy bunch of people and a sick bunch of people, so it doesn't really that much different. So what we did is that we implemented this in two ways. And so to show you the different data flows you get between an FHE application and an MPC application, this is quite a good illustration. So imagine that you had a homomorphic encryption variant. Okay, so this is how you would solve this problem using homomorphic encryption. So you have one computer, one independent computer comes up with a public key and a secret key, and they distribute the public key to the hospital. So the hospitals get the public key, so they're able to encrypt, okay? And the secret key, okay, yeah. Now, what the hospitals now do is they encrypt what they're called the contingency tables. These are whether the people did or did not have whether they're healthy or not healthy, and their specific DNA that you're testing for, which is basically a chi-square table. You encrypt the value of the chi-square table, and you send it to this server. Okay? So none of the data of the patients from this hospital goes to this hospital. None of the data of the patients from any of the hospitals goes to the server. Only the encrypted values go to the server. The server on the right. The server on the right computes the encrypted significance computation. Okay? The ciphertext, which is the encrypted answer, gets sent back to this server, who then decrypts. Okay, so that's the data flow. Now the reason you want to separate these two computations is that, and then you can then produce the answer, so you know whether the DNA position. So you get your result after you're trying to do research on. So the reason you have two servers is because if the secret key to decrypt was here, then as soon as when I got to this step, the server over here could just decrypt the output from this hospital and maybe deduce something about the patients in this hospital. Maybe the patients in this hospital are prone to the disease because they come from a poor area or there's something else associated to them. So that's actually breaching the privacy of the patients here, yeah? So this server is just aggregating all of the hospital information together, and only the final result of all hospitals together is decrypted, because only this one has the secret key. So these two servers have to be kept separate. And that's inherent, in some sense, in the FHE computation. Remember I said the person computing and the person decrypting are different people. So this is how you have to map it. Okay. Now, in the...
So this is MPC.
What's that?
This is MPC. Then.
It's sort of MPC-like, yes. So it ends up being MPC-like, so why is it not? Yeah. So why don't you use MPC, it's faster. Yeah, so... So here we have a different scenario. This is the MPC scenario, where here you have two or maybe three computers. The hospitals can secret share their contingency tables over to the servers here, who can then do the calculation, because they can do the privacy secrets calculation, and then just output the answer between them. Yeah? So you see, it's a much simpler architecture using MPC in some respects. And it's faster. Yeah. Okay, so there we go. You can do DNA sequencing if you want. Another one, which we're going to be presenting at the RSA conference next year, is what's called but we call EPIC because it's so cool. It's EPIC. EPIC stands for something. What's EPIC stand for?
Efficient private image classification.
Yeah, okay. Efficient private image classification because it's really quite efficient, private, and it classifies images. Okay. So what you want to do is you want to take a picture of something, and you want to analyse the picture and go whether it's, you know, I don't know. Suppose I'm taking pictures of animals. I want to know whether it's a cat or a dog. So I want to go, or maybe I want to know it's a car or a tank. You know, I'm kind of doing some other application. Okay. So this is what we want to do. We want to do image processing on encrypted images. So this is a bit like, you know, I have a bunch of encrypted images, and you can tell me whether it's an encryption of a cat or a dog with only ever seeing encrypted images. So it's a bit like a card trick. It's quite cool. Okay, so imagine this is the bunch of scenarios we have here. So you have an image holder. That's someone who has the image. I know, just take a picture of, you know, of the street. Yeah, and they take a picture of the street, and they want to identify the car that's in the street. They want to know, oh, I like that car. Haha, I'll take a picture of it. Oh, it's a Jaguar. That's what they want to know. They want to know that the car is a Jaguar and not some Rolls Royce or Mini or something. Okay, so that's what they're interested in. But of course, they don't want anyone else to know anything about the street. Then you have the person who's actually got the classification algorithm, say. So they've actually got a new super duper algorithm for classifying, or they might be searching for stuff that you don't want the image holder to know about. So it could be that you're taking some picture of some medical image, and your search and the classification algorithm provider is looking for a specific disease, and their detection algorithm is company classified or something like that. And then you've got the analyst who's going to learn the answer. So basically what we want to keep secure is the image, the actual thing we're searching for in some sense, the algorithm that we're actually using to do the searching, and we may want to actually also keep secure and provide to someone else the actual answer. So these two, so you could have the image server, image holder and the analyst being the same person, you could have the classification algorithm provider and the analyst being the same person, or there could be 3 different people depending on your scenario. But they're all going to be doing the classification using MPC. And this is super duper fast. We were thinking of having a demo today, but we didn't think there was enough time. But this is like we saw the demo earlier this week. Talk to Dragos if you'd like to see a cool demo. It's basically you go to Google, you select the image, you pump it into the program, and it tells you dog or cat, or yeah, you encrypt the image and it tells you what the image is without seeing. So it's kind of the best card trick you've ever seen. It's like, oh, you're thinking of a cat. I know what it is. Yeah, it's kind of really cool. Okay, so the previous best work on this was there's a bunch of test suites called Cyphar 10 and other which have been implemented in all sorts of different ways. We're 34 times faster without being 50 times improvement in communication costs. We're more accurate. We're better. We're faster. We're more accurate. We're just better, right? So in other, if we use the same accuracy, so if we don't try to get more accurate, we just have the same accuracy, we're 700 times faster. So that's even cooler. So it's going to appear at CTRSA. If you search for EPIC image classification online, you can see the paper. This is super duper fast, and so you can do image classification. You can do image processing on encrypted data. Now, there's a little trick here. The trick is the blue box. Okay, the blue box is a feature extraction phase where what we're actually doing is we're using what's called transference learning. So it turns out that in image processing and other applications, these huge neural networks that have been built by Google and others to do image processing are public, and they've spent gazillions of dollars producing these on their compute clusters, you know, with many images. And every time you go to an image, you go, oh, you know, it says select the road signs, select the street numbers. Yeah, this is you training its algorithms. Every time you go to this catch period, you go, oh, that's a road sign. You're actually training the neural network to use in the Google self-driving car. That's why they're doing road signs. Yeah, you're looking for a car. Oh, they're the cars. Oh, you're training the algorithm to spot where the cars are on the street. That's what you're doing. So those image processing neural networks are public, and they're for processing images. But what's amazing about them is they built them to do self-driving car, And you can use exactly the same neural network for another problem. It's what's called transference learning. You have a neural network you've learnt in one area publicly can be used for a completely different reason in a completely other area. So this is this bit can be done in the clear. So the heavy machine learning doesn't have you only encrypt the images. You only put it through the secure gateway after you've done the neural network. So it's there's a cool trick here with image processing you can use. You see, other areas can use the same thing, but that's what we're doing.
You talk about fast, is it minutes, seconds, hours?
You don't notice. It's microseconds, yeah?
Instant.
At most 1 second.
At most 1 second, yeah, it's basically it's like I type the term and it gives me the answer. Yeah, but it's fast, yeah, you don't notice.
Cool.
Yeah.
Does the classification algorithm need to be,
sorry.
Does the classification algorithm need to be tuned for this?
So the classification,
or is it a generic?
So the classification algorithm you choose. So the classification algorithm provider will train this specific classification algorithm for what they're trying to classify. But it uses generic features extracted from a generic neural network.
But you can use classification algorithm outside this MPC
but that's
application and then apply it.
The classification algorithm is standard. I mean, this is just standard. Yeah. In fact, it's very old, very old. Yeah. Okay.
And Nigel,
yes.
Classification then is done on feature.
It's on the features, yeah.
And do you lose something then?
Well, in terms of accuracy,
Yeah.
not much. In fact, actually, every image processing algorithm that you do the classification on the features, you never image process the whole image. It's just too many bits, yeah. So you always downsample using the feature extraction algorithm and then do image processing. The key point is that the downsampling doesn't really matter. It's trained, for modern algorithms, it's trained where a neural network, but it's just extracting features. Whereas in the past it would have been, oh, it's blue sky, it's a yellow ground, that's a beach scene. You know, now it's a bit more advanced than that, yeah. Okay, the other example, next example, will lead into what we're going to hear about this afternoon, maybe a bit of sepia, Jacob will talk a bit. It's about doing auctions. Now, you cannot have an NPC talk without talking about auctions, okay, because there's the famous application was about 2005, 2006. The first deployed NPC algorithm was about then, and it was deployed to get the clearing price of sugar beet in the Danish sugar market. Okay, so you have a bunch of buyers and a bunch of sellers, and you want to work out what the clearing price is. Now, okay, everyone kind of understands basic economics. That is where you want the price to be, right? It's the crossing of the supply and demand curve. So essentially, if you encrypt the supply curve, you encrypt the demand curve. All you're trying to do is you subtract one from the other, and you want to know whether the subtraction goes when it changes from positive to negative. Okay, so it's this binary search. Okay, assuming that they're monotonic, assuming that people in the market are not completely stupid, right? So we don't suddenly go, oh, you've decided to pay me more for this product. I'm going to produce less of it. You know, that's not, as long as it's monotonic, yeah, they're not stupid. So then you just have to go positive or negative. Okay, so this was an auction example. Now, auctions are a huge topic, and this is just one example, and you can do all sorts of different things. So one other thing we've been looking at is dark markets. Now, this is going back 10 years. I said that you were when I talked to investment bankers, and the reason is that it's about dark markets. About 40% of stock market trades in the world are done on dark markets, because it's not, so the high frequency trading is what's done during the day. But what happens usually if you have big pension funds or tracker funds, they have to rebalance every so often. They're following the Dow, and therefore the Dow moves a bit, and therefore they have to rebalance their portfolio to match the Dow, because that's what they said they would do. Or, for example, some analyst decides to get rid of IBM stock because it's boring, let's buy unbound stock, because that's really quite, apparently that's an up-and-coming one to go. So what you want to do is that you're about to sell shed loads of IBM stock. And if you say this openly in what's called a lit market, then what happens is you affect the price. I'm about to sell $1 billion worth of IBM stock, the price falls. Okay, so therefore, what I'm about to sell is now worth less. And then you have a downward spiral. And it turns out that the huge stock market trades, about 40% of them, are done what's called dark markets. Now, 10 years ago, when we went to see dark pool operators, they went, oh, this is not really a problem because everybody trusts us. Because you imagine you're a dark pool operator, what you do is you get the bids in, and then you go, you satisfy them, and then you hand out the answers. Now, if anyone's seen The Sting, you'll know there's the front-running scam. Okay, I got the bids in. I'm keeping it secret. I'm the trusted party. I got your sell for IBM. I'm now going to sell IBM before I execute your order. Okay, that's called insider trading. That is illegal. Okay, and this is the city, stroke financial sector. So if something is illegal, but they can make shed loads of money out of it, do they or do they not do it? Okay, right, so you've got it, right? So in the last few years, there's been a number of dark pool operators who have actually cheated at dark pool. So this is now much more interesting. And so we've been talking to a bunch of financial regulators and other people who do some work on how do we actually secure dark pools. Okay, so there's a question is, there's a real-time nature of market. So in the sugar beet auction, it was basically a once-a-year item, it was a sealed bid auction. Now, what happens when you're on a lit stock market, you have what's called a continuous double auction. Everyone puts trades in all the time, and the market changes as you go. Yeah. So you have a continuous double auction and a sealed bid auction, and we can implement the sealed bid auction. Can we implement the continuous double auction that's on the lit market? Now, we used our system that was developed in Leuven called Scale Mamba. Might in the end, if someone asks me, I'll tell you what the name is, but I won't stop the narrative there. So you have a continuous double auction method, which is the method for which you would normally use in the lit stock market. And this can actually cope between up to about 200. When we implement this in our system, we can, with a two-party MPC system, fully secure, deploy for tomorrow. We can do about 250 orders per second. However, it turns out that in dark markets, they don't actually implement the continuous double auction method. What they normally do is that they do a batching, because this continuous double auction is really for when you've got little trades coming in and it gives you the best spot price. So what most dark markets actually do, they do what's called a volume matching. They basically say, here's all the buyers, here's all the sellers, let's ignore the price information they want to buy, they just want to buy, they just want to sell, let's match the buyers to the sellers up in terms of when they've arrived. And then what we do is to get the actual price, we go to the lit market. So they go, so if you're selling IBM stock, so in this 5-minute window, say, here's all the buys orders, the huge buy orders, here's all the huge sell orders, let's match them together, they match them up, and then they take the price of IBM stock from the Dow, from specifically what that says. So you don't have to do a price calculation. This is how most dark markets operate, certainly in London and the US. Okay? So in there, we can do about 2,000 orders per second. Now, if you think about it, these are mega orders. These are not high-frequency trades. These are, we're shifting $300 million worth of Microsoft. We want to buy $100 million worth of Unbound. We want to sell, I don't know, what was we selling? I don't know, a bit of sepia, I don't know. Maybe buying a bit of sepia.
Don't sell.
Oh, buy a bit of sepia. I wondered whether he was awake. Okay, so this is pretty close to where we are. We've got a paper on this that we've submitted, and we've sent this to a bunch of. This is online. You can look about this online, and we're sent this to a bunch of regulators in the US and the UK to look at this, because that's where the big stock markets are. We don't know anyone in Japan, so okay. Okay, so that was one application. So another application, linking in to another one you're going to hear later, is statistics. So what you want to do is combine statistical information together, and this is basically what Cybernetica, we will be talking later about their ShareMine project. And there's been a number of applications, so Cybernetica, we'll talk about that. The City of Boston have done a gender equality survey where they got 200 companies in Boston to encrypt their salary information and then do a computation on whether they had gender equality across the city, and produced a bunch of statistics to do with gender equality in Boston, of the top 200 companies in Boston. There's the US government moved to what's called Know Before You Go, which is an act in Congress, and there's which is mainly driven by Senator Wyden, who's a senator from Portland, Oregon, who has been pushing MPC in US government applications, so much so that there are acts of Congress with MPC mentioned in them. Yeah, so he says, we will. So this is kind of cool. We've been working with Galway, which is based in Portland, which is why we've got the link with Senator Wyden. And the question is, so there what we've been looking is combining statistics, differential privacy and MPC together, because actually when you reveal information, so for example you do the salary information, you can reveal information about people. So imagine an example, I decide I'm going to work out the average salary of everybody in the room, so I work out the average salary of everybody in the room, and then I do a query with everybody bar you. Now I can work out what your salary is, yeah? So actually doing averages doesn't actually stop you finding information out. You have to add some extra information there, extra perturbation there, of course, called differential privacy. And in the DARPA-funded Brandeis program, we've been working on privacy-preserving stuff here, which we're basically using our MPC engine, a Galois-developed ternary writing thing, plus some differential privacy work by some US academics to produce a new system. And Jana is this secure database, combines our MPC work with a query rewriter from Galois, which takes SQL queries, dynamically rewrites them into the bytecodes used by our MPC engine, adds differential privacy to the top, and then adds some other US government applications, which I'll talk about in the next few slides. So this example was presented to they had a joint House committee on evidence-based policy making in the US. So this was the example that was given to them. So you could have the census data, the IRS, that's their tax system, and say they have some federal student aid. They could have their stuff in an MPC question, and then the policy MPC database. Then you could do policy queries on this by some policy wonk in Washington. You could do queries and therefore develop much better policy responses. Okay, so this was slide that was presented to the Senate, which was working on this. What do I want to say else here? Something else, I can't remember. I know, okay. And then this was then proposed in what's called the Know Before You Go legislation. So Know Before You Go legislation, is it worth going to a very expensive college in the US? Is it worth paying the fees? So this was very similar to the Cyberneticas example that I talked about, which is combining education and tax data. So here we've got US Census, we've got employment data, we've got loans and grants, we've got institutional data about how someone did in the college, and we've got the service record, GI Bill data, because you might actually be giving people special loans because they've just been through the army or something else. And then you do the analytics, and then you can provide data to the prospective student on whether it's worth applying to this college and taking out the huge loan. Similar thing here, talking about Census Bureau, both US Census, UK Census, and certainly I've heard the Dutch Census and a bunch of other censuses are looking at MPC to secure census queries for future census stuff, and we've been talking with UN Global Data Platform and other people to do census queries. This is big. And this, I just learned this week, there's another huge effort, multi-million-dollar effort coming out of Canada to do national statistics with MPC. So this is a big market at the moment. There's US Demo Healthcare, there's another slide that was presented as part of our work with the Brandeis program that we presented to the US government on different ways you could have a healthcare application, research data from hospitals combined, medical, a bit like our one we already did here, but this is with a general database. So we've got a general specific database, the JAMA database, that's been funded by the Brandeis program. Okay, so as we come to the end of my bit, I've mentioned all companies bar one, so the one is going to be even less. So who knows what an HSM is? Who doesn't know what an HSM is? All right, okay, no, you can admit, if you don't know what an HSM is, you are doing well. Okay, so this is the good answer. Right, HSMs are hardware security modules. They're neither hardware nor secure nor modular. Okay? So anyone who's used a hardware security module knows. PANTS, if you're a big bank, I've done some previous work with Barclays Bank in the UK, which has a huge HSM infrastructure, hundreds of HSMs, and their problem was that we did some work that we published ages ago with them, is that your HSM, you have a number of them produced by a number of, well, were in the past, lots of different companies, but are now all one. Thales and Genalto, they're all the same company these days, but there were many of them, and if you're a bank, you've got many different branded HSMs in your huge warehouse Okay, and the problem is, suppose, okay, that one looks the most boring, doesn't it? That's bull, right? They must be old. Okay, that's an old one, right? So this one does DES 64-bit keys, right? Doesn't even do triple DES. And CBC mode, if you're lucky, with 0 IV. Now you laugh, that's actually what the banks, when we did the work with Barclays, had, was a 0 IV, their lowest common denominator, HSM, had 0 IV, CBC mode, single DES, right? This one up here has GCM mode. Oh, wow. Right? Okay, this one has to talk to this one. Ah. Right, so what turns out is that, so certainly Barclays, you have to lower the lowest common denominator, okay, and then you have to use ship crypto, right? This is because they're hard. They're hardware. They're not modular. You can't interchange them, and they're certainly not secure. Because if you go to a nice little startup in Paris called what's it called? What's Graham's Steele's startup? CryptoSense. Yeah. CryptoSense in Paris just breaks the APIs of HSMs like no tomorrow. So they're not secure. They're not hard. They're not modular. They're just crap, right? Okay. So so one way of they're shit basically. Okay, now here's my favourite slide, okay, is that if you take a key, you can split it into many, and this is the opposite of MPC. So, this is essentially what Unbound does, which Unbound will talk about later, but the cool thing here, okay, there's two interesting stories here. Okay, the first thing is that one of the problems with MPC, getting it to be deployed in the real world, was the name. Is multi-party computation, because it kind of implies that you have multiple parties come together to do a computation, right? Now actually, as a business model, that's really hard to sell, because A, what are you doing? You're selling software, you're selling it to multiple parties, so you have to, multiple customers have to simultaneously agree they've got a problem to solve and they want to buy your software to solve their problem, and it's your software, not someone else's. Okay, this doesn't happen, right? Okay, so it was always a problem. How do you actually get, everyone goes, oh, it's a good idea to do. Well, we've got something, but how do you stand? Right, so then, so Yehuda Lindell, one of my co-founders, had this brilliant idea to turn it on its head. Is instead of actually having many people come together, what you can actually do is take someone and split them up. So that one party becomes many parties. And that, by splitting it up, you do the computation on the MPC, but you get extra security that way. Okay, so you take the one key, and you split it into many fragments, and then you can do the cryptographic operation on the many fragments without ever bringing the key back together. Okay, so that's kind of cool. So there we have a really cool thing, and so that's the idea. And as you see, it's a bit dark side of the moon-like. Okay. Now, when we were originally coming up with the name for Unbound, it was really called Diadic, but before we came up with the name Diadic, we thought, it's really like that. That's really cool. So we didn't think of names like Moon or Darkside.com, which would be kind of a bit sort of down with the kids or whatever. We thought Prism. That would be a great name for a company. That was 2 weeks before the Snowden revelations. Prism was the spying program. So we just, okay, so then that's why it's Diadic, so, and then Unbound. But anyway, so that's, so the other thing you'll remember is Dark Side of the Moon. Okay, so, other one is some more stuff that we'll talk about this afternoon. So I end with this, which is a copy of the Gartner Hype Cycle from 2007, because I didn't have the one from 2008. And this is the Gartner, so they produce lots of hype cycles for all sorts of bits of security and blah. So this is specifically the hype cycle for data security, okay? And there's 5 Gartner reports in 2008. And if you look at this, multi-party computation is on the up. I challenge you to find another piece of named cryptographic technology that has been worked with. You could go to crypto in Santa Barbara and listen to a talk, and it also appears on a Gartner Hype Cycle. Yeah, this is almost unheard of. Well, there's blockchain, I suppose. Yeah. So if you're here, this is where the money is. This is where you should be investing. Okay. This is where the startups are. Format preserving encryption. Okay, that's kind of. Okay, I'll give you that. 5 years ago, 6 years ago, that was at crypto, but
not much going on there really these days. And then we've got this. Okay, if you're here, I wouldn't bother investing here. This is done, yeah. So okay, database encryption. You know, that's the past. Data loss prevention, tokenization. You see a lot of things in GDPR of tokenization. This is last year's technology. Well, not last year's. This is last decade's technology. Yeah, you don't want to be there. You want to be here. So there we go. So we've got multi-party computation, infonomics, which I'm presuming is informatics for genomics, which we've already talked about today. So we're there as well. Hopefully, someone will mention something in MPC for blockchain. So we're also there. We've got that. DLP, I don't know what DLP is. But anyway, so as you see, this is the place to be. If your company is over here, then you need to move here rapidly. And if you want to do that, come and see us in Leuven. We'll help you move here. And that is the end of my talk. Thank you.
Thank you, Nigel. Are there any questions?
I'm Dimitri from Norway, not from here. I have a couple of questions. Many of the examples you gave are like simple arithmetics, addition to encrypted numbers. But what's like the type of functions that you can do? You said there are so many functions, so can you comment on
that? Basically, what's the level of complexity is what's called the depth of the function, which is how many. If you think of if you write it out as arithmetic, everything can be written as arithmetic. Yeah. If you go down to circuits, everything can be written as arithmetic. So go down to circuits. Yeah. So essentially, it's the depth of the function, not the width. So it's not the amount of computation you're doing; it's the depth that you do is the problem. And it turns out that there's a lot of functions with relatively low depth. Okay, so averages are standard deviations are like that. You can do computation. You can the standard test example for AES is AES doing AES in the encrypted domain. Encrypt AES on an encrypted key. Yeah, so doing encryption of AES where you have the encrypted key and no one finds out what the encrypted key is. That's what's the depth? That's about 60. Ish, depending on how you count it. So we can do depth 60 calculations, and they just happen in milliseconds. 20 milliseconds for a depth 60 calculation. We can do. So then you go. Okay, so I'm prepared to wait. I can go much more. Yeah. So it really depends on the application. And then the other issue is a lesson I learned from a crypto company many years ago is that there's no point optimizing stuff to death because fast enough is fast enough. So it really does depend on what the application is. So if I'm doing a database query and I'm doing some sort of histogram, actually when I compute the histogram, that's actually quite a lot of depth. But if I'm sitting at a terminal and I go, okay, compute the histogram, and actually the ping time from me to the server is going to be longer for some applications than the actual computation, so I don't really care. So it's as if the human notices in those applications and they don't. So it depends on the application. But you can do relatively complicated things, but you have to program things in different ways. So you can't say, right, here I've got this neural network computation, or I've got this computation out of the linear algebra library or whatever, and I'm now going to do it in MPC. Because the reason is the normal way of computing has if statements. And as soon as I do an if statement on an encrypted value, I actually have to evaluate both paths and then recombine both paths in an encrypted way depending on the value of the if statement. So what you have to do is start writing programs that don't involve if statements. So it's more of a programming challenge rather than here's a function and take it problem.
My name is Sven Triffinger from Robert Bosch GmbH. My question is, what is the relation between the software-defined methods in comparison to in silicon hardware, like SGX or something like that?
Well, SGX isn't secure, yeah? What do you want? So SGX has got side channel attacks. So if I was running it on an enclave on SGX on my machine, it doesn't actually give me full security. So I can run side channel analysis attacks against SGX. SGX is not designed
to be resilient against active attackers on your machine. So for example, I could, in an MPC thing, I could actually have you resident on the cloud, on the thing that's actually running one of the MPC engines, yeah? And even if you were there, looking at the code, not just looking at it in terms of side channel analysis, but actually saw every variable that's part of the everything about the program, everything coming in and out of that computer. As long as there was one computer you didn't control, you have no break into the system. So it's much, much more secure than SGX in that sense, and it's more, but it's less packageable on a piece of silicon. So, so you could make SGX side channel resistant, but that would mean you couldn't run x86 code. It's a bit like this is one of the problems of Intel's stuck with 8080 backwards compatibility, which is why all their problems in the last 2 years have occurred. SGX, all the Meltdown, Spectre, is all their backwards compatibility issues. So if you designing something from scratch, you could probably do it, but no one does that. It's too expensive. The other thing which is no interesting on this side channel thing, so NIST and at KU Leuven, we've got another project where we're kind of doing similar stuff with MPC, is we're actually putting MPC on a chip, where different parts of the chip are doing MPC calculations between each other, and then if you actually do side channel views of the chip, so you measure some power consumption or whatever, the fact that you can't actually get all areas of the chip simultaneously without perfect noise, without any noise or interference, gives you increased side channel protection. This is what's called in the hardware industry, it's called masking. So hardware masking in the side channel community is exactly the same as MPC. It is the same thing. So actually what we're trying to do in Leuven, and we're working with NIST on this, is actually merging these two areas together. And NIST have a workshop on this in March next year. Yeah, in Washington, just after that. Okay, anything else? Or one more? Yeah.
Related to deployment, so you also mentioned that it's a complicated problem. So basically with MPC you distribute the trust from one central party to several other parties. So this is already a difficult thing because yes, you don't trust one party, but why should you trust three parties that maybe they are in China, and plus you have the complexity of the communication, so the security of the whole infrastructure. And so even if this works, you have the complexity of getting those three parties. And can you comment a bit on how realistic this is?
Well, I would say you'll see this afternoon. We actually have companies that are actually selling products in this space to people now, which are actually using this. So the thing is it doesn't solve. It's not something you can take off the shelf for all applications. It's for very, very specific applications currently, which allows you to do this, where the business models, the trust relationships, all come into play to allow you to enable this. So what I said was this was a big impediment for MPC taking off. So you had from like 2007, when the sugar beet auction was done, until about 4 years ago. There's virtually nothing except for Partisia, which is the parent company of CPUR. Okay, and then from 2007, suddenly these trust relationships and business models all started coming together, and now I went to a meeting of twice this size in the US the other week. A third of the audience were government, a third of the audience were big companies, and a third of the audience were academics. Every academic had a startup. Yeah, every startup had at least $10 million of funding. Yeah, so there's space here. It's just suddenly gone completely mad because these trust relationships for specific niche applications are really beginning to come along. So yeah. Okay, last question then, because I'm...
Okay, quick one. About the state-of-the-art of fully homomorphic encryption. Is there such thing as fully homomorphic encryption for general purpose data, or is it highly input dependent?
Do you mean in theory or practice?
Well, practical.
No. 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 In theory, yes.
I know.
In practice, no. Yeah. Not yet. Okay. Okay, thank you. Let's go get some drinks.